Good evening, everybody. Thank you for joining us tonight for part 2 of Introduction to Statistics. A few housekeeping items first before we start. If you can hear me, if a few of you could just please click your hand raise button so that I can see that I'm being heard. Okay, I'm seeing some hands. Thank you very much. And just a reminder that after the webinar is over, we'll send you a follow-up email with a link to the slides, and also sometime tomorrow we'll also send you a link to the recording once that's available. And the follow-up email tonight will also have a link for you to fill out the post-webinar evaluation, and once you fill that out, you'll get a link to download your CME certificate for tonight. And with that, we'll get started. I'd like to introduce our Executive Director, Dr. Jane Orient, who will introduce our lecturer for this evening.
Well, welcome to you all, or welcome back. We are once again here together with Dr. Herman Walter Borg, who is a Yale-trained physician scientist. His specialty is neuroendocrinology. He has a wide range of experience in designing and leading research projects, including clinical investigations, basic research, and animal studies. Is particularly well qualified to talk to us about both descriptive and inferential statistics. Dr. Borg.
Thank you very much. Let us start. Good evening to everybody, and I hope you will enjoy this lecture. This is a second part of the lecture on statistics. In the first part of this lecture, we have discussed the significance of statistics for physicians, suggested the study strategies for learning statistics, presented the role of statistics in the scientific process, and review basic concepts of statistics, including sample selection and data collection, initial data manipulation, tabular and numerical methods of exploratory data analysis. Educational objectives for this lecture include discussing graphical methods of exploratory data analysis, presentation of basic methods of statistical inference, introduction of the most commonly used statistical tests, and providing direction for further study of statistics. We will start in the place when we have ended, that is, in discussing exploratory data analysis with a focus on graphical methods. In the table shown here, I have listed for you 10 most commonly used graphical methods. Graphical methods allow to discover trend in patterns that are hidden in the data set. So the list here includes the most commonly used graphics from the pie charts to QQ plots. Let's discuss them one by one. We'll start our discussion with a pie chart. It is a circular chart divided into sectors. It illustrates numerical proportion mainly. It is simple but flawed method. It is particularly unsuitable for large data sets. It's very difficult to deal when the pieces of pie become so small. It is also quite inconvenient for data comparison. However, due to its simplicity, it's commonly used in business. But for all the problems stated above, it's avoided in research. The next type of the graphical methods, line chart. As shown on the pictures on the left, a series of data points called markers connected by straight line segments make the line chart. It shows how data changes in time and in response to intervention. Therefore, obviously, it will be very useful in biomedical research. It reveals trends very clearly, as can be seen on the pictures here on the left side. Error bars added to the markers provide additional information about the data. For all that reasons, it is commonly used in research. Bar chart. It is useful for presenting discrete data. It uses horizontal or vertical bars to show comparison among categories. Axis represents categories versus discrete data, as it is shown on the pictures on the left. There are different types of bar charts. For instance, stacked bar graphs showed bars that are divided into subparts, as shown on the left upper corner of the picture. There are also grouped bar graphs. There are bar clustered in groups, as it's shown on the bottom part of the picture. There are very convenient ways of presenting the data, and they are commonly used in research and in business. Now, very important methods of graphic representation. Important and at the same time not very intuitive. And therefore we will spend much more time on this than on another graphical methods. It is called histogram. It is useful for presenting continuous data, used to show the data distribution. Histogram can be really confusing for physicians. What it does, it uses rectangles whose width represent class intervals called bins that is equal with groups into which the data are put, just like somebody would put something to the bins. The heights of those rectangles are proportional to the frequencies of the corresponding bins, of the data in the bins. Researchers use the word histogram very frequently, but one should realize there are actually two types of this graph. There is a histogram and there is a true histogram. Histograms are also known as a frequency plots, and true histogram differs from the typical frequency plot in the following way. True histogram uses rectangles whose widths represent class intervals with bins, just like frequency plot, but areas, not heights, are proportional to the corresponding frequencies. In true histogram, heights equal to the frequency density of the interval. That is the frequency which is divided by the width of the interval. But that leads to the very interesting thing, that frequency plot will be identical to the true histogram when relative frequencies and bins of equal lengths are used. Because then when you just do your calculation, you will get the same thing. Terminology of histogram is as colorful as a mathematician can invent. The term bins is used to denote class intervals, because indeed those are like a bins pictured here. Those are equal with the groups into which data are put, like somebody would put something into the bins for organization. Bins are also used to denote series of ranges of numerical value into which data are sorted. There are no best numbers of bins, and different bin sizes can reveal different features. It could be used to clarify the data, but obviously it could be also used to obfuscate and confuse. The next term, frequency, and I'm pictured here on the left side, the tally counter like one looks in the hematologic laboratory. It is basically a frequency, which means the number of observation in each class interval that is within the bin. I'd like to spend a few seconds on discussing etymology of histogram, the origin of this word. The term histogram sounds quite awkward for most physicians. It invokes the word histara, which is uterus, but this is just coincidence. The origin of histogram is actually unknown, and it was likely coined by statistician Karl Pearson as a combination of two Greek words, hestos, which means must or column, and gramma, that means writing. However, it is also possible that the origin was much less colorful, as simply histogram, the term histogram was used by Pearson to denote historical diagram. Because this figure can be confusing sometimes, let's consider how histogram is made. Well, histogram is a representation of a frequency distribution by means of rectangles whose widths represent class intervals and whose areas are proportional to frequencies, just like we discussed. So let's take a data set as pictured here. Not so big, but it looks messy enough. So let's try to make some sense out of it. In the first step, let's divide it into bins while noting the frequency of the data. And then we'll have this colorful picture just below. And let's use it to the plot. The assignment pattern here is as follows. Bin 1 contains data value of 1. So let's put it here. And because its frequency is 1, we will plot it on the y-axis. And so on. Bin 2 contains data value 2, 2. So the frequency is 2. Again, let's assign it to the x-axis, and let's assign the frequency to the y-axis. And the process is repeated. And that way, we have our histogram ready. But this was a very simplified way of making histogram. How real histograms are made? Well, in real data sets, most numbers will be unique. Let's consider much more realistic data set as pictured here. Let us use ranges as a bins. And by using ranges with width of tens, data can be organized as follows into this neat table. So in the first column, we have a data put into the bins, which are being assigned to the second column, which contains data range, and then we list the frequency in the third column. And then it is nicely and beautifully transformed into the graph shown on the right. Because many medical students, as well as even seasoned physicians, has a problem with reading histograms, let's give you 3 examples. Histogram allows to analyze data set by reducing it to a simple graph showing significance of primary and secondary peaks. That is the main use. So let's have on the picture presenting a histogram on the left here. This histogram tells us that in the data set, the peak is very well defined. We see a very nice big column here. It is close to median and mean. Outliers are not very frequent because the peak is towering above them. Thus, the deviation from the mean are not frequent. It's a pretty good data set. Let's consider a second example. Looks a little more as a Manhattan than the nice typical statistical graph. So what we can say about it, the peak here is not well defined. It is still fairly close to mean and median. Outliers are frequent, but they can be noticed. Thus, the deviation from the mean are frequent. There is something about this particular data set. It is either very diverse or the methodology used was flawed. Let's consider example number 3. Let's have a look at it first. What does it say? Well, this histogram tells us that in this particular data sets are 2 peaks, a taller primary peak and a shorter secondary peak. Median and mean are hard to localize in these data sets. And outliers are hard to be defined as well, because which one you pick. So what's our conclusion here? There is a very poor definition of signal if somebody was looking for it, or there are at least 2 signals in the data. The next device, which is a derivative of a histogram, is a frequency polygon. It is drawn by joining the midpoints of the top of bars of a histogram, as it's shown on the picture in the upper left corner. So basically you have a histogram, and then you can just draw the line joining the middles of the bars on the top. It is used to compare frequency distribution of multiple data sets on the diagram because it can be superimposed, which will be very messy if we want to try to superimpose a few histograms upon each other. Dotplots. In this method, data are plotted on a simple scale using circles. There are two types of dot plots used: Wilkinson dot plots and Cleveland dot plots. Wilkinson dot plots is used for univariate data. It is a simple representation of distribution. It is useful for highlighting clusters, gaps, and outliers in a small dataset. And indeed, a researcher can make it with a pen and pencil in the lab very briefly to see how his initial pilot studies are going. Cleveland data plot is quite different. It is used for multivariate data. It's a plot of points belonging to several categories. It is an alternative to a bar chart, so it really doesn't have much common with a Wilkinson dot plot. In Cleveland's dot plots, bars are represented by dots at the values associated with each category. So this is like similar with previously showed example with histogram and the frequency polygon. It's a simplified bar graph. It is mainly used in the business because, as it's shown on the picture on the left, you can use some fancy graphics to show your message. Now, we are going to discuss briefly mostly a historical and museal item known as a stem and leaf plot. Why it is called stem and leaf is illustrated on the picture in the left upper corner, because yes, it looks like a stem and leaves. So it consists of two parts. Right parts are leaves that contain last digit of the number, and left stem contains all of the other digit. It's a clever method that allows for visualization of a distribution in a small data set. And as one can see on the example on the left side, is useful for outliers and finding the mode. It was used very frequently in 80s because it was easy to make with typewriters, and typewriters were very commonly used. It became obviously less common after computer graphics became available, and one can create much more fancy graphs rather than relying on typewriters. Still, for your amusement, I emulated on the computer how the old-time researchers would convert a data set shown in the left corner, lower corner here, into a neat stem leaf plot. It really can provide a quite useful message about the data. Box and Whiskers plot has a similar significance to histogram in the sense that it is very frequently used, and it's very frequently misunderstood by physicians and by medical students. And therefore we'll spend some time discussing it. Box and Whisker plot depicts data from very quartiles, a concept that you shall remember from the first lecture. And I will just put a little picture here to remind you. There are different conventions that are used for the box in the box and whisker plots, and a different which are used for whiskers. Conventions used for the box are uniform, and usually there is no need to provide any explanation for those who know it. But the problem is that most physicians do not know it, and therefore it will be useful here to pay attention to it. The bottom of the box corresponds to first quartile, Q1, as you remember from the last lecture. The line inside is a median, that is Q2. there is a symbol inside. It's usually plus or star, and it's used to indicate mean. The top of the box is a third quartile or Q3. The height of the box indicates interquartile range. Width of the box is arbitrary as there is no x-axis, so it's just selected arbitrarily to visualize things better. And very important things, which is omitted frequently, spacings between parts of the box helps indicate the degree of dispersion, spread, and skewness, that is asymmetry, terms that you shall remember from the previous lecture. Let's talk right now about the conventions used for whiskers and outliers. Unfortunately, those vary and there is no standard. But usually, the ends of whiskers represent minimum and maximum of the data sets. Lower minimum, upper maximum. But also they could indicate one standard deviation above and below the mean. It can also indicate 9th percentile and 91st percentile, or the 2nd percentile and 98th percentile. Outliers, data not included between the whiskers, are being plotted with dots, circles, stars, or even lines. So the lesson here is because of this variability, the convention for whiskers and outliers should be described in the caption, and one who is looking at this graph should really look for that description in order not to be confused. So when and why the box plot is used? It can be used for univariate analysis as shown here, and let me just point your attention towards the light blue arrows and light blue description. Looking at this particular box plot, one can conclude that distribution is not symmetric because the median line is not in the middle of the box. I like to emphasize this thing because this is again a subject of common confusion. Also, box plot can be used for multivariate analysis. As shown here, we have two categories, male and females. And this example is a box plot for the height of 200 students by genders, males versus females. Looking at this, we can learn the following about the datasets. There is a difference in distribution of heights in males versus females, as very clearly shown here. At the same time, spread is similar across in both males and females because there are similar heights of the boxes in either side of the medians. Interestingly, there is more outliers here among men, as can be seen here, because there is much more lines here than in females. The next graphical plot, scatter plot, uses Cartesian coordinates to display values for two numerical variables. It is useful when comparing discrete variables versus numeric variables. Can suggest various kinds of correlation between variables. And it could be called one of the most honest plots because you pretty much present all the data sets. It is like looking at the data set from the distance, from above. And finally, quantile or QQ plot. It is used for comparing true to probability distribution by plotting their quantiles against each other. X-coordinate of this plot represents quantile of a first distribution, which is plotted against Y-coordinate quantile of a second distribution. If QQ plot is located on the line of a function y equal x, following that straight one, then two distributions are similar. If QQ plot is near the line but not perfect, then two distributions are linearly related. While QQ plot can be used for comparing any two different data sets, it's commonly used to compare an observed data to its theoretical model. So it is a quality control measure when you can see if your assumptive model is close to what you got in your research. Let's move now into the basic of statistical inference. In a contrast to descriptive statistics, statistical inference is drawing conclusions from data subjected to random variation, such as observational errors, random samplings, and random experiments. It makes conclusion about population by analyzing its sample as it's shown in the picture on the left lower corner. Statistical inference includes three very closely interrelated areas known as the propositions. Those are estimation, confidence intervals, and hypothesis testing. So let's talk a little more about the concept of statistical proposition. As we discussed previously, statistics reflects acts of interpretation, not absolute facts. Therefore, conclusions of statistical inference are statistical propositions, a mere proposition. They have a big meaning, but we shall keep in mind those are propositions. Final inference is obtained by using following interrelated propositions. Estimation. It is a calculation of the attribute of a sample statistic representing the best estimate of the attribute of population. That's parameter. We discussed that previously, that the statistic is an attribute of a sample and parameter attribute of population. Confidence interval, a second proposition, calculated region likely to contain true value of the attributes of interest. It indicates the reliability of an estimate. Finally, hypothesis testing. Consideration if a chance is a plausible explanation of findings. It uses the data to decide its hypothesis, but not any hypothesis, but a very specific statistical hypothesis called null hypothesis, that there is no relationship between measured phenomena can be rejected. And that brings us into the assumptions and modeling. Statistical assumptions are suppositions about mechanism and features of population and sample. Statistical inference relies on those assumptions. In this context, statistical model is a set of statistical assumptions. Assumption can be divided into non-modeling, assumption regarding population and sample, and modeling regarding distribution, structure, and cross-variation. And then bring us into extremely interesting and hot topic recently, namely parametric and non-parametric inference. Based upon modeling assumption, inference can be divided into the three following categories. Parametric inference or parametric statistics assumes that the population fits certain ideal distribution described by parameter. And I illustrated this by showing this nicely organized, put by somebody with obviously a compulsive disorder, stack of building materials. The second type, non-parametric, does not depend on the population fitting any parameterized distribution. So one could argue it is much more related to reality, and it shows that our building materials bricks in a disarray In the real world, when one gives a time, obviously one is much more likely to encounter a chaos rather than the order, and that we shall keep in mind. A semi-parametric method is a compromise, has both parametric and non-parametric components. Let's talk in more details about the parametric inference. It assumes existence of idealized distribution for population from which the sample is drawn, uses the known shape and parameter of this ideal distribution for the inference. A parametric inference is less robust but simpler than non-parametric. Let me just remind you the meaning of a word robustness. In statistics, it is used as a ability of a certain test to stand the chance or undue influence of outside factors. So, parametric inference is less robust as it makes more assumption than non-parametric inference. Now, if those assumptions are correct, it can give better estimates than non-parametric. However, if those assumptions are wrong, it could be very misleading, and therefore it is less robust than non-parametric. Overall, however, it is simpler. Its models are in general simpler than non-parametric inference. Thus, it is more convenient to use than non-parametric. And it is an explanation why parametric inference has been most commonly used. However, it became subject of a recent criticism. And I give you here, as a reference here, the book entitled The Black Swan by Nassim Taleb. It is not purely a scientific book, but rather an essay with an interesting musing on the parametric and non-parametric inference. So let's talk about non-parametric inference. It relies on no or few assumptions about the shape or parameters of the population distribution from which the sample is drawn. Non-parametric is particularly useful for study of population that take an ranked order. When compared to a parametric inference, non-parametric is frequently less convenient but always more robust. However, it has less power. We will discuss the concept of power, but in brief, it means that a larger sample size is required to draw conclusion with same degree of confidence when compared to parametric. And here comes a paradox. On occasions, non-parametric can be simpler than parametric. And this paradox is explained by the fact that if you think about the way of simplifying things by producing an idealized models, at a certain moment, your models became so complex and so elaborate that they overshadow your original concept. So on some occasions, non-parametric could be better. And therefore, non-parametric inference is seen by some as leaving less room for misuse and misunderstanding. Now, one caveat, a term non-parametric has additional meanings in statistics. For instance, it denotes techniques that do not assume that the structure of a model is fixed. Let us go over all the propositions that we discussed previously now in more details. We'll start with estimation. Estimation is using the data to provide a suitable guess at the population attributes. And there are several basic axioms that have to be memorized and understand well before proceeding any forward. The first one is a statistic. We discussed it briefly previously, but for the purpose of estimation, statistic is any mathematical function of the data in the sample. For instance, a mean. Estimator is a statistic for calculating an estimate based on data. So it is a process. Estimate is a result of an estimator, for instance, mean or variance. So estimate, it is a product of the process. Point estimator yields a single valued result. Interval estimator yields a range of plausible values. And finally, the concept of the error of the estimator. It reflects the degree of its precision and reliability. It depends on the sample size. Now we'll talk a bit about sampling distribution of the estimator, a concept which is actually relatively simple, but it's nightmarish for many physicians. Sampling distribution of an estimator is a probability distribution that describes the probabilities of the possible values for a specific statistic. The form of a sampling distribution will depend on the population distribution. Sampling distribution is important because it's necessary for constructing confidence intervals and hypothesis testing. As I said, those three propositions are extremely interrelated. And here it is, the simplest possible explanation of a sampling distribution of the mean, of a statistic which is of extreme importance when conducting research. Sampling distribution of the mean is a probability distribution that describes the probabilities of the possible values for the mean. And here how it's done. Consider a normal population. Take repeatedly samples of a given size from it. Then calculate mean for each sample, which will be known as a sample mean. Now each sample has its own mean value, and the distribution of these means is called the sampling distribution of the mean. And this abstract is illustrated in the pictures and tables shown on the left. So let's make a very simple and a typical for a probability theory experiment. Let's have 3 pole balls with the numbers on it. Then let's start taking 2 pole balls out of 3, returning them, and let's perform 9 of such experiments. Then we will have 9 outcomes as shown in the table on the left. Every time we'll take 2 balls, we will add up the numbers which are written on them, and then we'll calculate the mean for it. So the table on the left simply shows the number of outcomes with the means assigned to them. Now, those who recall the last lecture know how to convert it into the frequency table. So we'll build the frequency table which lists means, we've assigned to them frequency and relative frequency. And when we have that, it's extremely easy to make a plot shown below, which shows the sampling distribution of the mean plotted against relative frequency, which is a probability. Another important concept that is being confused not just by medical students, physicians, but also by statisticians and researchers, namely standard error of the mean versus standard deviation. Generally speaking, standard error of a statistic is a standard deviation of the sampling distribution of that statistic. Consequently, standard error of the mean, as shown in the formula on the left, is a standard deviation of the sampling distribution of the mean. So what is the difference between standard error of the mean versus standard deviation? Well, it is not so complex. Standard error of the mean estimates of how far the sample mean is likely to be to the population mean. So it is inferential statistic. In a contrast to that, standard deviation is a degree to which individuals within the sample differ actually from the sample mean. So it is a descriptive statistic. That's a difference. Another important axiom that we'll need to understand and memorize is bias of estimator. It is a difference between the expected value of an estimator and the corresponding population parameter. It is it was designed to estimate as it is shown nicely on the pictures on the left. We have two types of a biased estimator. Estimator can be said that it is unbiased, as shown in the left upper quarter. It is unbiased for parameter A if its expected value is precisely A. Estimator is biased for a parameter A if its expected value differs from A, as it's shown in the bottom part of the picture. Obviously, unbiasedness is usually a desirable property in statistics. And all this leads us to the absolutely important founding axiom of the modern statistic, which is a central limit theorem. According to this founding concept, the sampling distribution of any statistic will be normal or nearly normal if the sample size is large enough. Normal distribution is very useful for modeling, and therefore central limit theorem allows to make assumption about population if we assume that normal population is a corresponding ideal representation of it. And I'm showing you on the left so-called the Galton box or quincunx or Binet machine, which is used to demonstrate the central limit theorem. If you look at this, you'll see, well, indeed, it works if you have enough of little pellets here, and you will just put them to the funnel here. It will eventually distribute into the shape that is consistent with normal distribution. The most important and frequently used basic derivatives related to the central limit theorem are Z distribution and T distribution. Z distribution is a standardized normal distribution with an idealized mean of 0 and standard deviation of 1, as shown on this little bit complex picture on the left. Z distribution allows to create a compact table for all normal distribution, which were widely used before computer became available, but computers use the same table, just we don't see them. Another important word used by statisticians is a score. Score means a row score or a datum. It is an original datum that is observation that has not been yet transformed. Z-score or standard score is a number of standard deviation that a score or observation is from the mean of a population. It sounds pretty convoluted, but if you read it 2 or 3 times, then you can get it. Now, positive z-score means that the datum is above the mean, and negative z-score means that the datum is below the mean. So that's great. I mean, we have this model. Do we need anything else? Well, apparently we do, because there is a student t-distribution. It is a probability distribution that is used to estimate normal population parameters when the sample size is small or when the population standard deviation is unknown. Now, according to the central limit theorem, sampling distribution of statistic will follow normal distribution as long as the sample size is sufficiently large. Thus, when we know the standard deviation of a population, we can compute a very useful z-score and use normal distribution to evaluate probabilities with the sample mean. In reality, however, sizes of sample will be not large. They will be small sometimes. And on occasion, standard deviation of a population are unknown as well. So when either of these occurs, we have to rely on the distribution of the t-statistics, also known as a t-score. And that's a reason why student t-distribution is constructed. Let's move to the definite data analysis statistical inference concept known as confidence intervals. And I am giving you a very essential here for the reason that will become apparent after we'll stop talking about. Confidence interval can be summarized by the simple formula shown here on the left. It is statistic plus minus margin of error, as it is shown further on the picture on the right. Confidence interval indicates precision and accuracy of the estimator. Margin of error reflects observational error or measurements error, the difference between measured value of quantity and its true value. Confidence interval gives an estimated range of values which are likely to include an unknown population parameter. It is calculated from a sample dataset. If independent samples are taken repeatedly from the same population and confidence interval calculated for each sample, then a certain percentage, known as confidence level, of the intervals will include the unknown population parameter. Let's use the university analogy for that. Let's say that we are looking for a student of a certain height. However, we don't know his name. But what we know that he is living in a certain college. Let's say for Yale University, he's living in Davenport College. And that is analogy to your confidence interval. Confidence interval are usually calculated so that this percentage that is confidence level is 95% for the unknown parameter. Now, those are very important concepts which I'm going to tell you, and we deal with the value of a confidence interval. Width on the confidence interval indicates how uncertain we are about the unknown parameter, and it is shown on the left. As we can see, wide confidence intervals indicates that we are really less confident. Narrow confidence intervals means we are more confident, and they are associated with an n of a sample, with a number of observation or data subjects. Wide confidence interval implicate that more data should be collected before anything definite can be said about the parameter. This is this unfortunate words that any postdoctoral fellow dreads hearing from his or her mentor. We need more studies, more data. The very important thing about this concept, interestingly, confidence intervals, if you think about them, are more informative than hypothesis testing procedures. Confidence intervals provide a range of plausible values for the unknown parameter. Unfortunately, confidence intervals are underrated and underused in research. In fact, most medical journals prefer to rely traditionally on the p-value, and this situation is recently questioned. So let's discuss the last and the most critical for the research proposition, that is hypothesis testing. Hypothesis testing is a consideration, if a change, if plausible explanation of a finding. So if the things could happen simply by chance. It uses the data to decide if null hypothesis can be rejected. Null hypothesis states that there is no relationship between measured phenomena. Null hypothesis is contrasted by the alternative hypothesis designated as H1, which states that there is a relationship between measured phenomena. And the alternative hypothesis is typically the hypothesis of interest for the researcher. The other important concept are types of errors that happen when one performs testing of the hypothesis. The decision in hypothesis testing may be correct or may be in error. There are two types of errors depending on which of the hypothesis is actually true. Then we'll have, as it is shown on the table on the left, type 1 error. Type 1 error happens when the null hypothesis is rejected when it is true. Type 2 error is failing to reject the null hypothesis when alternative hypothesis is true. Type 1 error is particularly important. As we said before, it is rejecting the null hypothesis when it is true. It asserts something that is absent or false positive. The rate of a type 1 error is called the size of the test and is designated by the letter Greek alpha. It usually equals significance level of the test, also designated with the letter alpha. If null hypothesis is simple, alpha is the probability of the type 1 error. If we are dealing with a more complex composite null hypothesis, then alpha is the maximum of the possible probabilities of the type 1 error. The rate of type 2 error, in contrast to type 1, is called false negative rate and is designated with the Greek letter beta, and it is significant for a power of the test, which we will discuss later. One- and two-tailed tests and probability. Another important concept one has to understand before proceeding any further. Significance testing involves calculating the probability that a statistic would differ as much or more from the parameter specified in the null hypothesis as does the statistic obtained in the experiment. So it's pretty convoluted, but it makes perfect sense. So we can have two options. One-tailed probability, probability computed considering difference in only one direction, such as statistics is larger than a parameter. Two-tailed probability, on the other hand, is probability computed considering differences in both directions. Statistic is either larger or smaller than the parameter. And finally, we reach the core point of statistics, hypothesis testing process. And unfortunately, there is a lot of confusion about it, and many relatively good textbooks have an awful and very discouraging explanation of the process. Sometimes the multi-step and convoluted procedures are given, but in fact it is quite simple. And I'm presenting here the very efficient way of testing hypotheses that can be summarized by the 4 commands. And it goes as follows. Number 1, specify the null hypothesis. Number 2, select significance level alpha. Number 3, compute the p-value. Number 4, compare p-value with alpha. Let us talk about all those 4 steps in more details. Step number 1, specify null hypothesis. In significance testing, null hypothesis is typically the hypothesis that a parameter is 0 or that a difference between parameters is 0. For instance, the null hypothesis might be, in your particular research, that the difference between a population means is 0. Step number 2, selecting significance level alpha. The significance level is the highest value of a probability value for which null hypothesis is rejected. Commonly and traditionally, significance levels alpha are 0.05 and 0.01. So, for alpha equals 0.05, null hypothesis is rejected if the probability value p is less or equal to 0.05. Important point to remember here, this is all arbitrary, and it became the subject of a recent criticism. Next step, compute p-value. Probability value, known as a p-value, is the probability of obtaining a statistic as different or more different from the parameter specified in the null hypothesis as the statistic obtained in the experiment. Again, convoluted wordings. When you get a set of slides, you can just go and read it for those who have a less logical and mathematical aptitude. The p-value is computed assuming null hypothesis is true. The lower p-value, the stronger the evidence that null hypothesis is false. Traditionally, and arbitrary again, null hypothesis is rejected if p-value is less than equal to 0.05. And the next step, which is a direct consequence of all previous steps, is a comparison of p-value with significance level alpha. And as we mentioned already, if the p is less than alpha, then null hypothesis is rejected. An important set of comments here. Rejecting null hypothesis is not an all or none decision. The lower the p-value, the more confidence we have that null hypothesis is false. However, when p is more than alpha, findings are simply inconclusive because failure to reject null hypothesis does not constitute support for it. So the fact that we reject something doesn't mean that we automatically support it. It simply means that there's no sufficiently strong data to reject it. And this is an explanation for the pain of many researchers' experience that is related to the fact that one cannot publish so-called negative data. Well, when you use that method, you will really never have a negative data. You will have a truly positive results and then something that is inconclusive. Let us move now into the concept of statistical power that we have touched base very briefly before. The probability that the test will reject null hypothesis when alternative hypothesis is true is a statistical power. In other words, it is the probability of not committing type 2 error. If we would like to write the formula, then power of a test would equal 1 minus beta, as you recall from the previous discussion, when the beta is the rate of a type 2 error. Statistical power is also called sensitivity, is a function of a possible distribution determined by parameter under the alternative hypothesis. As statistical power increases, the chances for type 2 error decrease. power analysis can be used to calculate the minimum of the sample size required to detect an effect of a given size and effect size to be detected when using a given sample size. Isn't that neat? So statistical power is used to make comparison between different statistical tests, as we discussed briefly, between a parametric and non-parametric test, for example. And we approached the extremely important part of this lecture, namely essential of statistical tests. As we discussed it in the lecture number 1, the whole purpose of knowing statistics is being able not to conduct research only, but also to be able to properly appraise the value of statistical document, being it either a business document or research paper. In research paper, the focus is not on the testing, it is on the results. The statistical tests are mentioned only very briefly in material and methods. However, this brief mention may indicate if the paper contains valid research or not at all. And I made this little picture here showing what's going on. We have an elaborated scientific paper which contains numerous pages which are filled with graphs and with tables and with discussion. And among those so many pages there are 3 lines and 2 sentences which deals with statistical analysis. And here I give you a suggested methods of evaluating use of a statistical test either in the research or in the business document. The first question one has to ask, have the test been properly chosen? Number 2 question, have the results have been interpreted in the context of the test capabilities? And finally, when non-standard, a very complex tests are used, is their use justified? It brings memory of the formula of keeping it simple that we discussed in the lecture number 1. Here I give you a table that summarizes 8 most commonly used statistical tests. Obviously, the test that one encounters in his career will depend upon his or her medical specialty and the area of interest. By generally speaking, in biomedical research, there are 8 most commonly used tests, and it is a prudent way of approaching study of statistics by learning those 8 tests. And those include t-tests, specifically 2 sample t-tests used to compare means between 2 groups, paired t-tests used to compare 2 quantitative data from 1 subject, analysis of variance used to compare means between 3 or more groups, for estimating the degree of association between 2 variables, we'll use Pearson coefficients of correlation that we discussed previously. Please note that each parametric test has its sibling, so to speak, in form of a non-parametric test that can be used for testing the same situation. And when you're going to get the slides, I would advise really to concentrate on this table and read in more details the examples given. Now, the practical problem that I have as a lecturer here is that it is virtually impossible in the time given to me to discuss in details all those tests, as discussion of a student t-test would require a separate lecture, and discussion of ANOVA is probably suited for several lectures. However, that is actually a good thing because it allows me to introduce the way of a very simple method of assessing and comparing the various types of statistical tests then you can apply on your own to the test of your interest, as well as you can apply this method to assemble for yourself a set of the tests that you can rely on, as well as you can use this method to study any new exotic or unusual test that you encounter. And I will give you here a medical analogy, or even a little more, that makes it more complex actually, it's a medical business analogy. Let's imagine that you are at the same time an occupational medicine specialist and a director of human resources, and that you have a task of evaluating a worker. So let's say that that worker is a test, and you are an occupational medicine physician and a human resource director that has to evaluate fitness of that worker, that is tasked to perform certain work or to be put in a certain job position. So what you have to do under such circumstances, as both a specialist in occupational medicine and a human resource director, well, you have to create a form of documentation, like a patient chart, which will have sections such as history, such as physical examination, ancillary tests, and so on. And a similar method can be used to describe each single test. And then you can use it to cross-compare between different tests. And very unfortunately, statisticians do not use this method because they do not need to. We need to use this method. In brief, this method includes dividing in a reductionist fashion every test into a following characteristics. Number 1, type. Number 2, application. Number 3, correct use. Number 4, assumption. Number 5, procedure applied. Number 6, formula. And I will go over student t-test and ANOVA as a 2 examples that I hope will serve as a point of departure for you for your further own personal research and study of this area. So let's analyze a student t-test in this fashion. Type, it is a parametric test. Application, it evaluates if the means of 2 groups are statistically different from each other. Correct use, especially appropriate for the post-test only 2 group randomized experimental design. Well, this sounds convoluted, but actually it means what it means, and further explanation of this concept is explained in the addendum. But basically, it is the simplest method used in the biological research. When you have randomized group, you perform certain type of treatment on one of the groups, and you have a control. So that's a reason the student t-test is very frequently used in biomedical studies. Now, assumptions. Assumptions of a t-test are as follows. Population from which the sample is taken has a normal distribution. The variance of a population to be compared are equal. Procedure used by a student t-test. Examination the difference between means relative to variability of their scores. Formula use is a t-ratio. A t-ratio is a typical signal-to-noise ratio, and it is shown in the left part of the picture here, depicting in an absolute brief way how the t-test is done. So as we can see in the top part of the formula, we have a difference between 2 means, which is a signal. Bottom part is a measure of scores of variability, which is a noise. Calculated t is determined as significant or not by using table or a statistical software. Then analysis of a variance. As much as it's difficult to fit this ocean of methodology on 2 slides, the technique that I showed allowed to provide that useful simplified summary of this procedure. So let's start with the type. Type of ANOVA could be parametric or non-parametric. Application. it evaluates if the means of more than two groups are statistically different. Correct use of ANOVA requires use of a specific type of ANOVA for a specific scenario, in the way as it is listed here. One-way ANOVA is used to establish difference between two or more groups with one grouping, that is, assigning to group method. One-way repeated measures, when repeated measures are done in one group during the testing. Two-way ANOVA, difference between groups with a complex grouping methodology, complex way of putting subjects into the group, let's say. Two-way repeated measure is used for repeated measure structure with an interaction effect. ANOVA makes a numerous assumption, and I listed here the most pivotal ones. ANOVA assumes that the expected values of the errors are zero, that the variance of all errors are equal to each other, that the errors are independent from one another and normally distributed. Let's continue with our patient's chart of ANOVA, so to speak. So next feature is a procedure. The ANOVA is performed as follows. The mean is calculated for each group first. The overall mean is then calculated for all the groups combined. Within each group, the total deviation of each individual score from the group mean is calculated, and this is called within group variation, the variation that happened within the group. Next, the deviation of each group mean from the overall mean is calculated, and this is called between group variation, obviously. And finally, F statistics, the core of the ANOVA, is calculated and then brings us, in the natural way, into the formula feature of this test. The main formula of ANOVA is F statistic, which is the ratio between group variation to within group variation, between to within. It's F statistic. If the between group variation is significantly greater than the within group variation, it is likely that there is a statistically significant difference between the groups. The statistical software determines for us if the F statistic is significant or not.
Excuse me, Dr. Borg, I apologize for the very rude interruption here. We just got a notice from GoToWebinar that because they're having system-wide problems right now, and our webinar could end at any minute. And okay. So what I'm going to propose is we continue and hope that it doesn't end, but if we get kicked off, I'm going to email everyone. We'll get you your CME certificate for tonight, but we'll figure out a time to continue this at a later date if we do get kicked off. So with that, Dr. Borg, sorry about that.
Now that is perfectly understandable. The technology is a blessing, but it comes with the problems. So let us continue to the presentation of conclusions. Presentation of conclusion, in general, this step entails presenting graphical and numerical results and inferred conclusion from other step of data analysis in an accurate and concise form. In practice, specifically, it involves presentation of an abstract in the form of a poster or oral presentation, followed by preparation and publication of the manuscript, as that this process is shown on the left in the series of pictures. So we have reviewed all phases of statistical analysis successfully. And that leaves us with a direction for further study of statistics, in which I will discuss suggested resources. As we discussed previously, there is no single best statistical manual, because choosing the manual depends, number one, on the area that is of utmost importance for you, and number two, on your own personal characteristic, how much one is inclined to think mathematically, to think in the abstract or concrete manner, and therefore there is no ideal manual. Instead, a set of personalized references has to be assembled. My personal point is that electronic texts that contain hyperlinks or allow for the instant web searches for the specific terms are best suited for static statistics, as there are so many of those terms that are frequently not understood by physicians that it will be really very troublesome to carry a big printed statistical dictionary with us around. The following suggestions are examples of the text taken from the large pool of study materials, and some of those obviously are good and some are bad. This is not any endorsement presented here, but the mere suggestion of the manuals that I have found personally useful in the years of dealing with this problem. Harvard-Motulsky Intuitive Biostatistics, a Non-Mathematical Guide to Statistical Thinking, its third edition in year 2013. The title says it all. It is a non-mathematical approach to statistics written by a physician turned statistician, and it is written specifically for physicians. It is a very useful book indeed. However, Betty Kirkwood, Essential of Medical Statistics, is considered by many a classical statistical manual which has the least possible number of errors. And as you study this area, you notice that it is surprising for all of us how many of the statistical textbooks contain a very basic errors or inaccuracies. For those of you who are interested in the business statistics, I listed here two important business statistical texts as well, and they are listed here in gray. Now, there are tablet and smartphone applications that are designed to teach or allow one to review statistics, and I listed here a few of recent ones on three most commonly used platforms, that is Android, iPhone, iPad, and Windows 8. The market is changing rapidly, and the better new text and better new programs are available, and therefore it is useful to visit a store of whatever platform you have or prefer to use and search for the statistical application. I just give you here an example of an application I found useful. For the reason I stated before, namely, for the ability to search of unknown term, online resources are very good. And again, I give you two suggestions. The online statistic education, a multimedia course study, which is prepared by the Rice University, is a pretty good resource. As most of basic statistical text is not ideal, there are parts which are absolutely wonderful, and there are parts that are not as great. However, it is a good resource overall. A very good and concise introduction of statistics for medical students can be found on the link which I listed here. I also give you additional suggested reading, little more complex papers that we deal with the area of statistics of interest. I would specifically like to highlight the Black Swan, a famous essay dealing with the phenomenon of improbable phenomena and findings, as well as deals with robustness and fragility in statistics. So to conclude the part 2 of the lecture, statistics plays pivotal role in the science and business of medicine. Statistics can be abused and misused. Statistical illiteracy and innumeracy can be extremely detrimental for physicians and in turn for their patients. Study of statistics is challenging but unavoidable. Statistics is based on several sometimes very counterintuitive and complex principles of conventions. Those axioms have to be mastered first, which means very frequently they have to be simply memorized. There's no way around it. Statistics reflects acts of interpretation, not absolute facts. It is sad that many tend to forget about it. And because statistics reflects just mere interpretation, it is based on numerous assumptions. Understanding of statistical assumption models is critical for appraisal of statistical analysis. Statistics continue to evolve as methodology. For instance, reliance on parametric statistics and validity of a p-value based hypothetic testings are being recently questioned. I would like to acknowledge the help of my mentor, Dr. Stephen DeCherney, a professor of medicine at UNC School of Medicine, as well as a professor of business statistics at the UNC Business School. I have no potential conflict of interest, and the floor is now open for questions and comments if we are still online.
We are. We thank you very much, Dr. Borg, and we did manage to stay online, thankfully. And if there are any questions now, if you would like to ask them verbally, just raise your hand. Otherwise, you can type them into the chat box. I'm going to go ahead and paste the link for the evaluation form into chat, and if you'd like to go and fill that out after we wrapped up here, you have the link. We'll also email it to you in about 10 or 15 minutes, along with a link to the slides. And then, as I mentioned, tomorrow we will have a link to the video available. Okay, let's see. Any questions out there? I'm not seeing any questions at the moment. Oh, yes, someone just asked if it will be available on video, and yes, it will. And we will get you the link tomorrow. It won't be available probably until tomorrow, but we'll get it to you then. Let's see, I'm taking, okay, here we have a question. Could you comment on multiple comparisons? Let's see, that question is from Dr. Orion. I'll bring her on the line here and she can ask it verbally. Dr. Orion, are you with us?
Yes, and in the techniques that often used of data mining and data dredging, a lot of comparisons will be made once you have the data set that are not based on your initial hypothesis. And you can easily find things that have a p-value of less than 0.05 by chance alone. Is there not a formula for if you're going to make multiple comparisons that you really have to use a higher standard of significance?
Dr. Borg, are you there?
Hold on, Emma. Can you hear me now?
Yes, we can.
Okay, there's some. Okay, yes, I actually wanted to have a clarification of this question because it's a very good and very important question that's related to many areas. Multiple comparison is very useful in many branches of medicine, but it has been heavily misused indeed in the business. Unfortunately, the theory, which has been produced recently, mainly by the business statistician, became so convoluted that some compare it to the methods used by the Enron, so-called statistician specialists, who use mathematics to obfuscate the financial meaning. And pretty much the multiple comparison method became as an old-fashioned high-pressure liquid chromatography. I mean, you can really dial up the way of the results you want to obtain. There is unfortunately not a universal stand-alone formula that could avoid that. The careful analysis of each procedure and the understanding of fragility of typically used p-value is required to criticize those methodologies. So the best way of approaching a situation when we're dealing with a multiple comparison schema being used is simply ask for a specific methodology used and then go on with individual assessment. Unfortunately, there is no standardized simple formula to override it, and very frequent, the reason which it's used is that it is very difficult to debunk. I hope that that this answer is satisfactory.
Okay, thank you, Dr. Borg, for that. And just a quick comment, if you look in your chat window, I've pasted the link. In addition to the link to the evaluation forum, there's the link to the slides are now available in the chat window too. We will also email both of those to you shortly. Okay, now, all right, I'm checking one more time for questions. It looks like, well, we don't have any at the moment. We are getting some comments in the chat room that this presentation was very much appreciated. So thank you, Dr. Borg, for yet another excellent presentation tonight.
It was my pleasure.
Okay, and please stay tuned, everyone else, for an email follow-up, and we will be scheduling another webinar shortly and hope you will join us for the next one, and we'll get you the details soon. All right, thank you again, everyone, and good night.